My name is Elektra Wagenrath. I'm an activist in community networking and mesh networks. If you have been previously in my presentation about OLSR and beyond, you can also get that slideshow on that address that is printed here on the screen. Well, the picture for the introduction is a tower located in Bangladesh, where people share a VSAT, a satellite link to the internet for voice over IP communication mainly. Don't get confused, this is not Wi-Fi. That giant dish is necessary in Bangladesh because the satellite link has a very long wavelength and hence the dishes must be very huge. Also, they have very bad weather conditions during tropical rainstorms, and even with a 4-meter dish, the link goes down if the rain comes too heavy. Well, why would somebody want to build a wireless infrastructure with cheap Wi-Fi devices? It's cheap, that's the first answer. It's democratic and can be used by community activists to build community networks. And of course, there are many more motivations why you could use Wi-Fi for long distance. I'll show you how it is possible. The background of the slide is a town in Bangladesh. If you look closely, you see many, many towers. That's the reason, because in developing countries, Wi-Fi is already really widespread. People are not using it for surfing on the sofa, of course. They invest lots of money and build high towers and set up long shots. So, how? Finally, the beef. The most important thing is free line of sight. And a decent and good line of sight includes a clear Fresnel zone. Don't be confused by this word. I'll introduce you to that. You need good and powerful Wi-Fi networking cards that could be switched into a non-standard 802.11 mode. Some cards, they even work in the standard modes. There are some limitation in theory in 802.11. First of all, I have to mention here the acknowledgement issue that prevents, in theory, that 802.11 link is longer than 1.2 kilometers. You need antennas with a lot of gain, and of course, directional antennas. A long shot with Omni is hardly possible because you pick up a lot of noise. What is extremely important and the source of failure for most people that try to build long shots is that they don't properly mount the antennas, especially water protect the cables and plugs. I'll give you a very, very short introduction to electromagnetic waves. If you have a conductor where current is floating through, maybe you have AC with 50 hertz. With a measure instrument, you can see that electromagnetic forces are traveling away from that wire at the speed of light. The electromagnetic waves, they consist of a magnetic force and an electric force, and they are located crosswise onto each other. The polarization could be twisted, so we could have the electric force here and the magnetic force there, or any angle in between, and some fields are even rotating while they propagate. This is the fact if you have circular polarized antennas. Well, like a water wave, you can imagine electromagnetic waves if you view the magnetic field or the electric field. I assume now the electric field as a wave where the polarity travels from 0 to negative to 0 to plus to negative over time. And these waves, these electric and magnetic forces, they travel through space at the speed of approximately 300,000 kilometers per second. And if you have a wave that changes 1 time per second, that means the wavelength is exactly 300,000 kilometers. So if you have a wave that changes 100 megacycles per second, the wavelength is 3 meters. And the wavelengths that we use for wireless LAN at 2.4 gigahertz are 12 centimeters long before they pass through one complete cycle. At 5.8 gigahertz, it's approximately 6 centimeters. The most important thing if you plan to do a long shot is, like I mentioned it before, a decent line of sight. Those waves, they behave like light, so if there is an obstruction where the light cannot pass through, also your waves are blocked. With plenty of power, you may penetrate a few walls or a little forest even, but if you plan a link that should go further than a few kilometers and you don't start connecting an amplifier that is unbelievably expensive, it would not work. So nobody is going to build a link without free line of sight, only for a short distance. I had that problem recently. We did a link, it's 2 kilometers through a forest, which is in theory impossible, but we used antennas with very, very high gain, and it works, yes. But it's with very high gain, and it's not legal to do this in Germany. If you're new to the matter, what is quite hard to understand maybe is the issue of the Fresnel zone. I'll give you only a basic idea about it. There's more complexity to it. You can search Wikipedia for Huygens and refraction to learn more about it. It would be too much to tell you in a few minutes. The Fresnel zone is an area between the antennas in 3D that looks like ellipsoid. The reason for the Fresnel zone is that the waves are reflected by objects or refracted by objects that are within this Fresnel zone. This leads to waves that travel a different path than the direct path here, and that means that they travel a longer path usually. Of course, they have to travel a longer path. And this could lead to the effect that different parts of the energy that you emit on one side accumulate on the other side at your antenna that are within or out of phase. We have this dark blue wave. It travels the direct line of propagation, and this wave was reflected somewhere. It's quite strong, it had some good reflection. This could easily happen if you have metal parts in the Fresnel zone. And so it's quite strong, and it's out of phase. So this energy which is going down, it subtracts from the energy that you want to receive. And it's absolutely possible, and it happens very often, that the sum of all those waves, because we're just viewing one single reflection, deletes completely the energy that you want to receive. Like I said, it's not just a single wave that gets reflected in the Fresnel zone, it's numerous waves, and yeah, they come within and without a phase. In theory, they can amplify your signal, but in practice, they won't. They just add up to a noise floor that reduces your signal to noise ratio, and therefore you cannot have a proper reception and proper data rate. The Fresnel zone is the most difficult issue to deal with if you want to do long shots. In theory, it's possible to do even with Wi-Fi long shots that exceed more than 300 kilometers. But the problem is we have an earth bulge, and the Fresnel zone is growing. So you would need infinite high towers to do this. Some people, they made an extremely long shot. There is a race for doing the absolutely longest shot. What they did, they launched a balloon and they had a 6-watt amplifier and they were able to have more than 300 kilometers. The rule of thumb is that 60% of the Fresnel zone must be kept clear of obstruction at least. It would be better to have 80% clear Fresnel zone, but 60% is the minimum. Like I said before, you need very high towers if you want to go to very long distances. So it's the most expensive problem if you want to plan or do a really long shot. In Bangladesh, we solved the problem by erecting towers of up to 35 meters. Here there is a very simple formula to calculate the radius of the Fresnel zone where it is thickest. It's 0.5 multiplied with square root of the wavelength multiplied by the distance. We do some example calculations later. Yes, well, this slide just underlines the fact that it would be nice to have at least 80% free Fresnel zone. In some cases, you can easily achieve that, but in most cases, you will be happy if you manage to have at least a 60% free Fresnel zone. It's important to consider the terrain roughness of the terrain that is between the antennas. There is a difference between a flat surface or an urban area with small houses or the center of a town with such big towers, because you have lots of metallic objects that add a lot of reflections, and these reflections, usually they won't help you, they would just reduce your signal to noise ratio. There are very complicated models to calculate this. I use a rule of thumb, and the values that I use are printed here. You can download a copy of this presentation and have this information, and of course there's a lot more resources on the web. How to deal with the Fresnel zone? As you see, if the frequency goes up, the wavelength goes down. You remember that I told you that with a frequency of 1 Hertz, 1 cycle per second, the wavelength would be 300,000 kilometers. So a link at 5.8 gigahertz has a significant smaller Fresnel zone area than a link at 2.4 gigahertz. So one measure that you can use to reduce the thickness of the Fresnel zone is to increase the transmission frequency. So move to the A band. But this is an issue. In most countries, it's illegal to use the 8-band outdoors or even use it at all. Trade-off of using a higher frequency is that you need a bigger rain margin, because waves at higher frequency are more affected and attenuated by rain and moisture. Something that helps your antenna at the same size has 3 dB more gain at double frequency, because the reflector is bigger if you use a dish, but that's the default for long shots. The next problem that makes it necessary to have really huge towers is the earth bulge. I have these 2 blue-gray lines. That would be the mathematical line that hits the horizon and hides objects that are behind the horizon. If you would be on a boat on the water, you would see another little boat in a distance of about 12 kilometers. In fact, this mathematical line would suggest you can only see the boat